Hi, so this is the video that covers this section that we would have covered tomorrow in class, section 7.3. All right, so this is the only section we cover out of chapter 7. It's on the hyperbolic functions. Very, very similar to the trig functions. You will find, if you remember derivatives and antiderivative rules for the regular trig functions, that these are almost identical. All right, so these are functions that are closely related to the trig functions and also to exponential functions. The connection here is that the regular trig functions are defined based on relationships involving our unit circle. The hyperbolic functions are defined based on similar relationships for the hyperbola. This is the equation of the unit circle, x squared plus y squared equals 1. If you change this sign in the middle to a minus, this becomes a hyperbola, x squared minus y squared equals 1. Okay, I wrote these down here for the main identities. You really aren't going to use those in this section. Okay, we'll revisit the regular trig function identities in chapter 8, but these are just what they look like when we're dealing with hyperbolics. Those aren't really needed for any of the homework problems though. I just put them there just so you have them. Here are the basic definitions. So the hyperbolic cosine and the hyperbolic sine function are both defined in terms of the exponential function e. The only reason you need this definition would be if you have to evaluate and you don't have a graphing calculator with the hyperbolics built in. Most graphing calculators have those built in, so you wouldn't need to use the E definition. Or if you are doing a problem where the answer involves something of these two forms, sometimes it converts back to a hyperbolic function just to get it in a more simplified form. Okay, so anyway, the sine and cosine hyperbolics, it's just cosine followed by an h means a hyperbolic cosine function of x, and then sine followed by an h is a hyperbolic sine function, right? All the others are the same. It looks like the regular trig functions with an h at the end. All right, so the cosine is defined to be e to the x plus e to the negative x divided by 2. And then the sine is e to the x minus e to the negative x divided by 2. So those two have exponential definitions. The other four are defined just in terms of regular identities. So the hyperbolic tangent function is hyperbolic sine divided by hyperbolic cosine, just like it is for regular tangent. The cotangent, same thing, cosine hyperbolic divided by the hyperbolic sine, same as it is for regular trig functions. Hyperbolic secant, 1 over hyperbolic cosine, and hyperbolic cosecant, 1 over hyperbolic sine. So these are really just more helpful if you have to use those to help you integrate, okay, or differentiate if it's helpful to rewrite them. But they're just no different than the regular reciprocal identities for the other functions. All right, if you have to evaluate, at least the hyperbolic cosine, sine, and tangent are built into your calculator. Some calculators may have the others, but not all of them. You can find those in your calculator's catalog if you need to use those for evaluation purposes. If you can't find them or you don't have a calculator that has them in there, you would have to use this definition to evaluate. So in other words, if you wanted to do hyperbolic cosine of 0, you could plug 0 in for x here. Or if you can find that function in your calculator's catalog and pull it up, you can just type it in your calculator and it will evaluate for you. Okay, we can talk about that in class on Monday. All right, so we need to understand how to differentiate and integrate hyperbolics. That's basically the homework in this section. All right, so here are the rules. Notice they are very similar to the regular trig function rules. The derivative with respect to x of the hyperbolic cosine of x equals hyperbolic sine of x. I put an asterisk by this one because if it's not hyperbolic, the derivative of cosine is negative sine, but in the hyperbolic version, it's not negative. So that one is slightly different. Derivative of sine is cosine for hyperbolics, just like for regular. Derivative of hyperbolic tangent, hyperbolic secant squared, again, just exactly like the rule is for the regular trig function. Hyperbolic cotangent is negative cosecant squared of the hyperbolic. It's exactly the same as regular cotangent. Hyperbolic secant of x is negative hyperbolic secant of x, hyperbolic tangent of x. This one has an asterisk because without the hyperbolic, it's also opposite, right? It's not negative if it's not a hyperbolic, but in the hyperbolic, it's opposite sign. And then the hyperbolic cosecant is negative cosecant cotangent, hyperbolic version. Okay, so all of these are exactly the same as the regulars, except for this one is opposite in sign, and so is the cosine. Okay, going backwards, same thing. Antiderivative of sine for hyperbolic is cosine. Antiderivative of cosine is sine. Since neither one are negative in the derivatives, neither one are negative in the antiderivatives. If you had to integrate hyperbolic secant squared, you get back to tangent. Hyperbolic cosecant, you get negative cotangent, or cosecant squared is negative cotangent. Secant tangent, negative secant, and cosecant cotangent, negative cosecant. Okay, I just wrote those down so you have them. Okay, again, if you remember the regular ones, and if you don't, you need to go back and relearn them, because come chapter 8, you have to know them. Okay, there is no way around it. We'll have 2 entire sections of all trig, okay, when we get to chapter 8. All right, so we're just going to run through some just examples of finding derivatives and antiderivatives. All right, find the derivative of each of the following. F of x equals the hyperbolic cosine squared of x. Okay, all right, so this means it's the hyperbolic cosine of x to the second power. So this is going to require a chain rule. The power rule brings down the 2 to the front. So you get 2 in front. You keep the hyperbolic cosine here. This becomes a first power times the derivative of the inside, which is the hyperbolic sine. So you get 2 hyperbolic cosine x times hyperbolic sine of x. Just by chain rule, and you're done. All right, over here we've got square root of hyperbolic cotangent of 3x. So the first step is to rewrite that as the hyperbolic cotangent of 3x to the power of a half. And then again, we're going to use the chain rule a couple of times here. So the 1/2 comes down to the front, 1/2 in front. You keep all this like it is. Subtract 1 from the power gives me a negative 1/2. Then you take the derivative of the inside, which is another chain rule. Derivative of hyperbolic cotangent is negative hyperbolic cosecant squared of the inside function 3x. And then again, because that inside is not just x, you multiply by its derivative, which is 3. So there are 2 chain rules happening on that problem. So to clean it up, you've got a negative 3 and this hyperbolic cosecant squared of x on top. This 2 is on the bottom, and I'm going to move this whole thing down to the denominator to make it a positive 1/2 power, which puts it under the square root. So that's just simplifying. All right, this one again, chain rule, natural log of hyperbolic secant of 2x. So the log function, the derivative is 1 over whatever's inside, so 1 over hyperbolic secant of 2x, times the derivative of the inside. So the derivative of the hyperbolic secant is negative hyperbolic secant of 2x, hyperbolic tangent of 2x, and then its inside function has a derivative of 2. Okay, so we had to use the chain rule twice again. Notice the hyperbolic secant of 2x here will cancel with this term on the bottom, leaving just negative 2 and the hyperbolic tangent of 2x. Okay, one more derivative. Here, x squared times hyperbolic tangent of x. This time it's not a chain rule, but it's a product rule. So the first function is x squared times hyperbolic tangent of x. So they take the derivative of the first is 2x times the second function, hyperbolic tangent of x, plus the first function, x squared, times the derivative of hyperbolic tangent, which is the hyperbolic secant squared. So just product rule. Not really much you can do for simplifying that. I guess if you learned to factor out an x, you could, but that would be about it. All right, so again, regular derivative rules, product rule, possibly quotient rule, lots of chain rule with the new definitions. All right, antiderivatives. Okay, indefinite integral, evaluate integral of hyperbolic secant squared of w times the hyperbolic tangent of w. So we should recognize from this integrand that the derivative of the tangent is the secant squared. So we're going to let u be hyperbolic tangent. du then is hyperbolic secant squared. So replacing those within the original, this is my u, and then all the rest of this stuff is the du. So you just end up getting u du. Antiderivative then is u squared over 2, and then you put back the original function, hyperbolic tangent squared over 2 plus the c. All right, next one, this is a definite integral. 0 to 1, hyperbolic cosine cubed of 3x times hyperbolic sine of 3x dx. So again, remember that the cube here means that you're cubing the entire function. Hyperbolic cosine of 3x all cubed times the hyperbolic sine of 3x. So this is in the inside of the third power, so that's going to be our u. Its derivative then is hyperbolic sine of 3x times the 3 by the chain rule. So that part of it will replace this, but you got to divide both sides by 3 because there's no 3 here. So 1/3 du can replace this part of it. So your integral becomes, this was your u, so you get u cubed, and then all this stuff is the 1/3 and the du. All right, so to change your limits. So I just showed how to do it using your definition, okay? You could have also used your calculator. Be careful though, we'll talk about why here I didn't simplify. So if I plug in 0 for x here, you get hyperbolic cosine of 0. If you're using the definition that involves e, that's e to the 0 plus e to the negative 0, which is still 0 over 2. So this is 1 plus 1 on top, so that's 2 over 2, which is a 1. So the bottom limit turns into a 1. If you can find the hyperbolic cosine function in your catalog of your calculator and pull it up on your screen, then you can just insert 0 and press enter, and it should tell you it's 1. All right, when you do that for this one and you plug in 3, like if I had e to the third plus e to the negative third over 2, that is some decimal that is not nice, right? It's not a rational number. Your calculator would also tell you that if you used your calculator function. Okay, so they want an exact answer. So in that case, when you don't get some nice rational result, just keep it as hyperbolic cosine of 3. Okay. There is one in my math lab for the homework that is like this, and they'll expect you to keep that as a limit. All right, so once I get to here, I just finish it with u. So u add 1 gives me a 4th power. Dividing by 4 makes this a 12 on the bottom. And then evaluate between our new limits. So we have the 1/12 in the front. This becomes hyperbolic cosine of 3, right? That gets plugged in here to the 4th power. Minus, and then when I plug in a 1, I just get 1/12. And then that's it. Just leave the answer like that. All right, here's another one with an indefinite integral. E to the hyperbolic cosecant of x times the hyperbolic cosecant hyperbolic cotangent of x. So this, right, is a form of the derivative of this. So let's let u be the exponent of e. Its derivative is negative cosecant cotangent. So we just don't have the negative there, so negative du will replace this stuff right here. So there's the negative and the du to replace what I underlined, and otherwise this is e to the power of u. This becomes antiderivative then would be itself, and then you just plug your u back in and then put the plus c at the end. Almost all of these are going to be some type of u substitution. All right, and then one more, we'll do one more definite integral. So integral from 0 to natural log of 2 of the hyperbolic tangent function. This one, so the hyperbolic tangent is not the derivative of anything, right? You don't get this from taking a derivative. Okay, so you have to rewrite it in order to see how to evaluate it. So you can use your one of the identities that says that tangent is sine over cosine. So we'll write it like that. Now we can let u be the cosine on the bottom because the derivative of that is the sine, which sits on top. All right, so if you let u be hyperbolic cosine of x, derivative is hyperbolic sine of x dx. So when you replace your integrand, you get a u on the bottom, and then this thing on top right here is just du, so it becomes 1 over u du. All right, so we have to change our limits. So I showed over here the work if you're changing them using the definition with the e's All right, you could also have just used your calculator and it should give you the same results. All right, so hyperbolic cosine of natural log of 2 for that upper limit would become e to the natural log of 2 plus e to the negative natural log of 2 all over 2. So e to the natural log of 2, right? The natural log has base e, so this simplifies to just a 2. This will, but I have to move this, log property tells me that the coefficient negative can be moved up to the exponent, so I can shift this coefficient of -1 up to the power and make that exponent, rewrite it as natural log of 2 to the negative first. The reason we do that is, again, so I can simplify like the first term. E is the base here and e is the base here, so it should simplify to just 2 to the negative first. Well, 2 to the negative first is a half. And then the 2 on the bottom. So a half plus a half is 5, or sorry, 2 plus a half is 5 halves. And then divide that by 2, so take half of that, gives you 5/4. So this one does simplify to a rational number. If you find your cosine hyperbolic function in your catalog and pull that up and put in natural log of 2, it probably says 1.25. And if you ask it to convert that back to a fraction, right, that's the same as 5/4. All right, and then here again, the bottom limit was 0. That was, we had converted that before. If I plug in 0 for x, e to the x, or e to the 0 plus e to the negative 0, that's 1 plus 1 over 2, which converts or simplifies to 1. Okay, so these are our new values. So an antiderivative of 1 over u is natural log of u. Evaluate between 5/4, or from 1 to 5/4. So natural log of 5/4 minus the natural log of 1. Natural log of 1 is 0. So you just end up with the natural log of 5 over 4. All right, that's pretty much it. Just know how to evaluate antiderivatives, indefinite and definite integrals, and find regular derivatives of the hyperbolic functions. Okay, all right, so that is it for section 7.3. So that means on Monday we will be ready to start chapter 8.